I'll bet you $20 I can make that curtain move from all the way across the room.
All the way
$20.
over there?
Come on. That purple polka dot thing over there?
Let's see.
Blue duct tape holding it up.
I don't believe you.
Check this out.
Whoa!
Okay.
How did you? Oh! Oh! And how are you doing that?
Okay, so I'm just pushing on the door here, opening and closing,
Oh yeah.
close, open, close.
I see it.
Okay, and what's happening?
Good question.
I can also do it from over here. Oh, this one has one of those things that slows you down. Okay.
Oh yeah, I see that.
Yeah. So what is happening? What's in between that door and that window right there? The air that we breathe. Yes. And so my first question for you guys is, what is air made of? What is air made of? Well, we know it's made of oxygen and nitrogen, carbon dioxide, water vapor, and a whole bunch of really insignificant trace amounts of other elements. Yes?
It's made out of molecules.
Yeah, molecules.
Particles.
Okay. And what are those molecules doing?
I can't see them.
What are they doing? Oh, no. Okay. No, I can't see them. Okay. They're microscopic. We can't see them. But what are they doing? And essentially, they are moving.
They're moving. They're in constant motion.
Yeah, even though we can't see them, they are moving. So at STP, the molar volume of air is 22 liters, and 1 cubic meter is that many liters. So how many cubic meters are in 22 liters? Let's do this. So 22 liters. That's what we're trying to figure out. And we're trying to go to
Cubic meters.
1 cubic meter. Okay, so we said how many
1,000.
liters are in there? 1,000. Okay. Oh, there we go. All right, so I'm just gonna do, I don't need this. So 0.022
Cubic meters.
Cubic meters.
And let's see, 0.022 cubic meters.
Okay, so 22 liters is 0.022 cubic meters, all right? If a cube has a volume of 0.022 cubic meters, oh, what a cute little cube. What is the length of one side? Don't you have a cube in here? Oh, I thought you had this cube. Oh, here we go. Okay, we're asking, what is the length of one side? If this was 0.022 cubic meters.
What's the relationship between the volume and the length of the side?
Isn't it like length times width times height? Like
Yeah.
Length
And if they're all the same, it's cubage.
Cube, so that means we need to take the cube root of this, right? Okay, so that's that math button for 0.022. Okay, I get 0.28 meters.
So that's 28 centimeters. That's this long right here.
Right there?
28.
28 centimeters. Okay. So if a cube has, so our cube, that cube has a length of 0.28 meters, or, oh wait.
Yep.
Yeah, is that right? Or 28 centimeters.
That's the length of one side. 0.28
yes.
meters. That's a big cube.
Okay, so now, if 1 mole is that many particles, and this is 1 mole.
Wait a minute, isn't that avocado's number?
Avocado! my chemistry peeps remember this. Hopefully, you better remember it. So if 1 mole is 6.02 times 10 to the 23rd particles, that occupies that much space. How much volume does 1 particle occupy?
How many cubic meters per particle?
Okay, so I'm gonna go ahead and do that right here. So we'll do 6.02 times 10 to the 23rd particles, and we're gonna divide it by the 0.022 meters cubed. That's going to give us a particle in,
How much size, how much volume one particle of
Yeah.
air occupies.
6.02 times 10 to the. I haven't got to my mole unit yet for chemistry, but it's coming this year. Okay, so I put that in correctly there. 0.02. So I get 2.74. 2.74. How much volume does one particle occupy? Meters cubed. Particles per.
Wait a minute.
Is that right?
No, we want cubic meters per particle.
Oh, so we need to switch these.
Yeah, we got to. You know what you do? Take your hit answer, hit x to the negative 1.
Oh, nice. Where's my -1 button on here?
It's right above the squared.
Right there. Thank you, sir. And to the -1. Okay. To the -1,
If
people.
you flip, because we want to know how many cubic meters per
Oh,
particle.
that's more like it. Okay. 3.65 times 10 to the -26 meters cubed per particle. Okay, so how much volume does one particle occupy?
A very
One
tiny
particle-
little thing.
Yeah, I was looking at this and I was like, this many particles per meter cubed? I was like, okay. All right, so
That was my bad.
if a cube has a volume of 3.65 times 10 to the -26 meters cubed, oh, look at that. What is the length of one side?
Well, we found that before by taking the cube root, yes?
Yeah, okay, so let's just do that. So math 4, so I'm taking the cube root of my answer, and I get 3.32 times 10 to the -9th meters.
-9 meters, nanometer. Ooh, that's a nanometer. That's 3.32 nanometers.
3.32
Nanometers.
Nanometers. Whenever you have to the -9th meters, it's just a nanometer. Okay. What's next? Let's see. The length of the side of this cube is 3.3 nanometers. That's what we got. Average size of an air molecule is about 0.3 nanometers. What does this mean?
Well, now hold on a second. What is all this stuff we've done? We've got 1 mole of air is 22 liters. That's a certain number of cubic meters. And 1 mole is 6.02 times 10 to the 23 particles. So what we've done is, if you have, is how much volume on average one particle occupies. And it's that 3.65 times 10 to the -20. So that's a cube of a very small size, much smaller than this. And what's the length of one of those sides? Well, it'd be 3.32 nanometers, or 3.3 nanometers.
Length of one side.
So we've got a tiny little box that the air particle occupies, but the average particle is 0.3 nanometers.
Okay.
So,
What does this mean?
well, that means, let's see, if you got 3.32
How many can
nanometers, so that particle is going to occupy about 1/10.
So there's some space around it, right?
Yep.
Okay.
About 1/10 of the volume is occupied by that particle.
Okay. The average distance an air molecule travels before colliding with another one is 68 nanometers.
Oh, so these particles that are moving around, and they are moving around,
They're
that's
moving, hard to
kinetic molecular theorem,
Whoop.
they're knocking into each other.
And this is called the mean free path.
Yeah, that's the mean free path
Okay.
before they whack into something.
So what you're telling me, Boykin, is that if we imagine every air molecule, whatever it is, being inside of a box, it would take up this much space, and this one side has a length of 0.32 nanometers. But you're saying that the average distance an air molecule travels before colliding is 68 nanometers?
Yeah.
Okay,
And
so that means the other one's over here, right?
Well, that's because the particles are moved randomly, and most of the space is empty.
Yeah. So these particles are moving. There is lots of empty space relative to the size of the particles. And they're running into each other.
That's right.
Yeah.
So we need to know something about the motion of particles and what air is in order to answer this question.
So thinking about everything we've just talked about, how did the motion of the door cause the curtain to move?
You were over here. Something went all the way across the room and made the curtain move.
So what's happening here? We have air molecules that are in the room, right? And essentially what's happening is they're whacking into each other.
Yeah.
And what's different between, this motion and this motion? What's happened to those air particles?
Well, when you open the door, you increase the volume right there,
Okay.
which stretches the particles apart.
Uh-huh.
And particles from over here move into that open spot.
So as I open the door, take a look at that thing. Okay, everything's being pulled this way, and you can see
Well,
that
that's not
everything.
completely right. You
Ooh,
have
true,
the
true.
air right here is low pressure, stretched apart. The air next to it moves in, which leaves low pressure over here. Air over here moves in.
Now, what's this you're saying about moving into low pressure? It has to do with density, right?
Yes, it does.
So it's gonna, your air particles are gonna, I don't know if this is correct, but want to kind of reach an equilibrium. So they travel from high to low.
Well, the pressure is let's not talk about pressure.
No pressure.
well,
It has to do with density. Believe us.
Well, no,
okay?
but it is density
Yeah.
and pressure. You have low pressure right here. Air from over here rushes in to fill that low pressure, which leaves low pressure over here. Air from over here rushes in, and that propagates all the way across the room till it reaches the curtain over there.
So it's kind of like it's a stretch.
It's a stretch.
Okay. Was there a physicsy term we used for that?
It's rarefaction. Rarefaction, Scooby-Doo. So what happens when you pull the door in?
Well, when I pull the door, and now I'm compressing.
You're squeezing the
Squeezing.
particles together,
Yeah.
and they stretch apart. They whack into particles over here, which stretch apart. They whack, and that collision travels all the way
Yeah,
across.
and you can see because when I close it, well, it's hard to see it there, but you can see it.
Well, if you go back and forth,
Yeah.
so you push and pull on the door, that pushes and pulls on the air, and the push and the pull propagate across the room and push and pull on the curtain.
Now, I did want to add something because I think you mentioned this weekend. The air particles aren't really like moving all the way across the room, right?
That's an excellent point. No.
Yeah. And so, we'll actually, we should show them that simulation. I can add it in.
Okay.
I can add it in at the end of the video. I'll have you guys click on the little simulation that we added above, and push play. It'll ask you to subscribe.
Well,
don't subscribe.
It'll give you about 30 seconds
Yeah.
of the sim, and then it'll say subscribe.
Yeah, so check it out above, and it has one red particle in it, right?
Yeah.
And you can see the stretch in the squeeze that happens.
And the particles are just moving back and
It just
forth.
stays in that one spot, and that's really important.
Yeah.
Okay, so how did the motion of the door cause the current to move? Well, got particles whacking into each other, squeezage and
Stretching.
stretching due to changes in density.
So that is a kind of a sound wave. It travels the same as a sound wave. It's just very low frequency. So this is a good question.
So is a sound wave transverse or longitudinal? Not transverse, remember when we were playing with our slinkies. And longitudinal was more like this way.
Yeah, you've got waving like this and it
Yeah.
goes in that direction, or waving like this and it goes in that. Oh,
Yeah. Let's show it up there. Transverse.
okay. By moving my hand back and forth, I'm sending waves, compression waves, longitudinal waves down that come back and forth. So, what is sound?
So sound is a longitudinal wave created by a vibrating object. And I mean, it makes sense, right? Because we just talked about like how particles are being squeezed and stretched,
Yeah.
In this direction and then that direction by opening the door, and they're all moving this way,
Yep.
right? So sound is a longitudinal wave created by a vibrating object. In that case, it was the door that was our vibrating object.
Yeah.
The vibrating object pushes and pulls on the medium, increasing and decreasing its pressure locally, like in that one spot.
And we got a speaker over here.
Yes, we do. And so this speaker is on top of a record player, and you can see, so the speaker will move when it's producing sound, move up and down.
There's a paper cone on the inside of here.
Can you see that right?
Yeah, it's easier to see from the other
Yeah.
side.
Oopsies.
You got the cone that moves back and forth to make the sound.
And you guys have all seen that, right? I mean, when you hang out in your friend's, new car, and you see the speaker, they've got the whole thing blaring, boom, 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 right? So you guys have all experienced that at some point. If you haven't, maybe you gotta get some better friends. That was good. Okay. So this is a visual. You've got the speaker here, and you've got your ear here.
Yeah.
And this, of course, has the vibrating cone, and we can see the particles when the cone moves this way, like the door being opened. It creates that low pressure area right here.
Where the particles are stretched apart.
Yeah, and they're going to start to move that way, right? And this is that high pressure. They move this way. These ones are moving this way. And you can see how it creates those areas of high pressure and low pressure.
And what happens when it moves this way, it squeezes them together. That's like a high pressure. And when it moves back, it stretches them apart. That's like a low pressure. So you have high pressure, low pressure, high pressure, low pressure that travels through the air.
And so let's talk about this sine wave here. Wherever the high pressure points are, which are these denser, darker spots, that correlates with the crest of our sine wave here.
Yep.
Okay, so high pressure, and then these would be low pressure areas.
Yeah, you could think of it, it's very difficult to visualize a longitudinal wave. Transverse waves are easier to see. And if you could think of this as a graph, a pressure graph, high pressure and low pressure, high pressure with a compression, low pressure with a stretching, then this is a good way to visualize how that works.
There we go. How do your ears work? Oh, let's take a look at this guy over here. Okay, is this a good spot for it?
Yeah.
Okay, so let me get over here. Okay, let's take a look at the ear. So we have, this is your ear. This is your earlobe. No. Okay, so you got your outer ear and you've got your inner ear. And it's separated by this tymphatic membrane in there. Can they see that right? And what happens is, so you've got sound that comes in, that longitudinal wave. And there's these three bones.
Well, what happens is that eardrum moves back and forth just like the window did.
Yes, just like the window did, yeah. And from there, we have those three bones. What do you call them? The hammer or the...
Hammer, the anvil, and the stirrup, I think.
Stirrup, yeah. It's been a while since I took anatomy. And those transfer the vibrations, very, very sensitive to all frequencies, to here, to our cochlea. And this is that snail shell thing that it also has to do with balance. But what happens is this cochlea is lined with little microvilli, which are just kind of like little hairs.
They're little hairs.
And
just like hairs on your arm, when the wind blows, you can feel it. There's a nerve at the base of every hair. There's a nerve at the base of every one of those little hairs inside the cochlea.
And they all lead to this guy. And so, your ear, your cochlea, the microvilli in your cochlea are able to sense, the different frequencies of a sound that comes in, lower frequencies here and higher frequencies in here. And so, as you get old, well, first of all, do those things that if something were to happen to any of those, Mr. Boyd can speak from experience now. Are you able to regrow your microvilli?
Do they grow over the course of your lifetime? No, they'd be
don't.
filled up with.
Yeah.
You know what I just noticed here? I noticed we've got the x-axis, the y-axis, and the z-axis right there.
Oh, cool.
That's how the ear does balance. You've got a fluid-filled thing in the 3 axes.
Yeah, the ear also has to do with balance. The ear
It's
is
an
a
amazing,
really cool thing.
It's an amazing thing.
So the microvilli in your ear, you're born at a certain point, you develop them, whatever, I don't know the timeline. But you don't, if something were to happen, if you were to break them due to loud music, you go to a show, or you play your headphones too
You
loud.
got the earbuds in, you got
Yeah.
them cranked up all the way. Enjoy it now, because when you get
Yeah.
into your 40s, it'll be, what?
Yeah, so
What?
what happens is you lose that sound at a certain frequency.
Yeah.
Right. And I wonder, you know how when you get once you're like 14, you can't hear that dog whistle thing anymore. I wonder. I don't know.
It's older than that.
Okay.
Yeah, we've already seen this. Go
Yeah,
ahead.
that's your eardrum, your tympanic membrane. So sound requires a medium, solid, liquid, or gas to travel through. Okay,
Yep.
so let's take a look at the general relation for all waves. So the general relation for all waves is the wavelength is going to be the velocity over the frequency. Also, we know that frequency is the inverse of the period, so we can use this equation.
And where does this equation come from? You want to show them where that comes from?
Yeah, so we should have talked about this in class, but just in case I didn't. Okay, so
Speed is distance over time.
speed equals distance over time.
Yeah.
And when we're talking about wavelength, what's our distance?
Well, for waves, it would be the wavelength, which is the Greek
Yeah.
letter lambda,
And then for t, it will be
the period.
the period, right? And so that equation right there, and I'm gonna write this right here. Velocity equals wavelength over t is really it's exactly right there. You
Yeah.
know, multiply by t. Okay, you've got that one right there, and that's the same thing as saying v over t like this.
Yep.
Oh, sorry, v over f, frequency. My bad. Okay, take that. put it
Because
into one
period
of
and frequency are the inverse of each other.
And so, I mean, when I was doing physics in college and whatnot, I just used this equation, but I always had a hard time remembering it.
Right.
And so Mr. Boykin just showed me this, and I think it's fantastic.
Speed is distance over time. For waves, what's the distance? The wavelength. What's the time? The period. Boom to boom.
And you work from there, okay? Waves also travel a certain distance in a certain amount of time.
Yeah.
So speed equals distance over time, where this speed is the speed of sound, maybe in air or water. This is a specific number
Yep.
that is known. So yeah, it's
Two ways of looking at it, and you have to choose which one is appropriate to the situation you're looking at.
Yeah, you gotta read the question. You
Yeah.
understand what it's asking. Here's the question. Okay, so it says, a sound wave produced by a clock chime is heard 515 meters away, 1.5 seconds later. So distance equals 515 meters. The time is 1.50 seconds later. What is the speed of sound in air?
Which one of these expressions that include speed in it are we going to use?
Well, we want to use this one
Agreed.
right here. So speed equals 515 meters over 1.50 seconds. Okay, 515 divided by 1.50 seconds. And we get 343
343 meters per second.
meters per second. And then the wave has a frequency of 436 cycles per second. What is the period?
That's the inverse, isn't it?
1 over t. So we can just say, what do you just 1 over
436.
436 CYC over SEC.
There you go.
Trying to
Southeast
CYC.
Conference.
So 1 divided by 436. Oh, 436. Is that right? 436? Yeah. Okay. And I get point. What's the little number? 002.
002.
Seconds per.
Is it exactly 0.002?
No, it's 0.229. Should I put them all in there?
Yeah.
0.0. Okay, we'll go. We'll just move this over a little bit. 00229 seconds per cycle.
All right. So seconds per cycle, that's a frequency.
Right.
Now we want to know the wavelength. Which one do you want to use here?
Well, we need the one with the wavelength, right?
Yeah.
So we've got wavelength and we have the frequency from before. Do you want to use the frequency or should we use our
No, it
newly
didn't give us the
calculated-
frequency.
Okay.
Oh, well, we just calculated it. Sorry.
Yeah.
Sorry, they did give it to us.
So let's use this one right here, right?
Yeah.
So let's go ahead. You said you use frequency.
Why not?
Yeah, you could also use this one if
It'll
you
give you
wanted
the
to.
same answer.
But you know, in case you messed up, we don't make mistakes, right? No. What was my? Here we go. 343 meters per second over the frequency, which is 436 cycles. CYC.
It's about 3/4, isn't it?
Okay.
0.7, 0.8.
Looks like it. 343 divided by 436, and we get 0.79.
0.79. That's this long. That's 0.79
Nine.
meters. That's the
Okay.
wavelength.
So there's the wavelength. The speed of sound in air is 343 meters at 20 degrees Celsius.
This is a number that we'll use over and over again, unless we're given something else.
And that is what we calculated here
Yeah.
on purpose, because this is a known, value.
Yeah.
It's in the book. We'll show you later. Okay.
Should we show them the speed of sound and the other thing? No, that
Oh,
comes later.
Sorry. We said to do it. Not yet.
Okay. All right.
Oh, just needs. Okay. An echo is a sound well, I feel like I just hated you guys. An echo is a sound that travels to a surface, bounces off, reflects, and comes back to the source.
You ever heard an echo?
Echo.
Well, we can demonstrate an echo right here with the
Oh,
slinky.
Yeah. Okay, so an echo would be like, so it goes to the source, bada boom, and then it comes back, echo, right there.
You know, do it with a transverse wave.
Yeah.
Do it with a pulse.
Okay. Right. And there we go.
And
Audible.
comes back and echo.
Right? So it goes there and it comes back. So what does that mean for the distance? For for a distance d between a source and the reflecting surface, an echo travels 2d.
It has to go down and come back.
There and then back, right? So let's take a look. Let's see, I'm gonna use green. So a hiker shouts toward a vertical cliff 685 meters away. The speed of sound in air is 343 meters per second. And the distance equals 658.
85.
Oh, sorry.
You got it.
Oh,
No,
I
you
wrote-
wrote it right.
Yikes. How much time before the echo is heard?
Which
Okay.
equation are we going to use?
Well, we want to know time, and we've got speed and distance. We're going to use this one right here. So that's time equals d over s. And we're going to, it's an echo, right? So
It has to go down and come back.
So we'll use 2d right here. So we'll do 2 times 685 divided by our speed, which is 343 meters per second. 2.68. Oh, sorry. 2 times 685 divided by 343, and I get 3.99.
3.99 seconds. That's a good echo.
The wavelength is 0.75 meters. What is the frequency? Okay, well, we need to use the one with frequency, so that's going to be that one right there, yeah?
Uh-huh.
Okay, so frequency equals the velocity over the wavelength, and our velocity is going to be 343 meters per second, and it told us the wavelength was 0.750 meters.
Yeah.
343, our new favorite number, divided by 0.75. Okay, 457. 457 457
cycles per second or hertz? Cycles per second or hertz are the same thing.
Second.
All right.
Okay. The speed of sound is determined by the restoring force of the medium carrying the sound.
Yep. You ever heard, been in the water, been in a swimming pool, and somebody tap on the side and it sounds like it's right next to your head?
This is the one where we want to show you, Mr. Boykin. So that means that depending on what you're traveling through, it's going to affect the speed, right? And so FYI, the speed of sound varies in media. Is it working?
I'm waiting for it to focus.
Get my hands out of there.
Well,
All right. Hey, anyways, so you've got air at 0 degrees, it's 331, and air at 20 degrees, it moves faster, 343.
yeah.
Water, 1,493 meters per second. Seawater, it moves faster.
It's a different density.
And we've got iron. Wow, iron, 5,103 meters per second. That's fast.
Yeah. So and the difference between those is the restoring force bringing things back towards equilibrium.
So for some it's right?
Yeah, that's right.
Okay. Oh, that's a really good thinking about when we're opening, closing the door, the stretch, the pull, thinking about it as a restoring force.
Yeah.
Okay. If the speed of sound in air is 343 meters per second, how long does it take to travel 1 kilometer? Go ahead and get started on this, ladies and gentlemen.
1 kilometer is 1,000 meters. So we want to know time. Let's see, time is going to be distance divided by speed, right?
Yeah. Okay, and how far are we going? 1 kilometer is 1,000 meters?
1,000 meters.
And it's in air.
343 meters per second.
Okay, that's just going to be 0.343 seconds. Right? Bada boom. Okay.
Is it?
Is that right?
1,000 divided, no, it'd be, let's see, yes, distance
Wait, hold
over
on.
speed. No, it's not going to be 343.
1,000. Oh, you're right. Wait. It should be divided by 1,000 if that's the case. It's 2.992.
Aha. Hey, we never make mistakes.
It's one of those days.
It is a
seconds.
Monday.
Yeah, wait, what number did I just say? Oh, that would be such a short amount of time anyways. Yeah. Okay, so at the speed, way to check. Does your answer make sense?
1 kilometer is takes about 3 seconds for the sound to go that far.
Okay.
But I don't speak kilometers.
Oh. Wait.
No.
Oh, yeah.
I know miles, I know feet, right?
The United States has brainwashed us. Anyways, okay. If the speed of sound in air is 1,125 feet per second, how long does it take to travel 1 mile? Because this is how we think, right?
Well, we need to, 1 mile is 5,280, so that's the distance.
5,280 miles, right?
Feet.
Oh, sorry, feet. Is in 1 mile.
Yeah.
Feet, okay. And we want to know how long does it
So the speed goes on the bottom, 1125.
1125 feet per second. That's going to give us the seconds that we want for our units. Here we go. So 5,280 divided by 1125, and I get 4.69.
4.7. Let's call it 4.7 seconds for sound to go a mile.
Seconds. All right, sweet.
Come on.
Come on. How could we use this to estimate how far away lightning is?
Now, there are places that have thunder and lightning and have rain. You know, we don't have much rain here in California for crying out loud.
Yeah, I used to live in Indiana and it was thunderstorms all the time. So,
Yeah.
So this means that about every 5 seconds, if you hear
It goes a mile in about 5 seconds.
it goes about 1 mile in 5 seconds. So, so it goes about 1 mile in 5 seconds. So if you were to hear thunder,
Well,
you count 5 seconds.
Well,
or
first,
like-
when you see the flash of lightning, start counting.
Yes, there you go.
1001, 1002, 1003, 1004, 1000. That means that the lightning is a mile away, and lightning is dangerous. If it's less than 5 seconds, you need to take shelter.
Yeah. Man, it's been a while since I've seen like real rain and lightning.
Yeah.
So I was like 7 years old. No, I was like 5 years old when I lived in Indiana.
Oh.
Lots of rain and thunder.
We're not going to do this.
Yeah.
We're done.
Oh yeah, we're done. Okay. So what you guys are gonna do is for homework, you're gonna do page 352.
Out of the regular physics.
Regular physics textbook, and you're gonna do numbers 1 through 4. Go ahead and do them, you guys. Get them done.